Welcome to Team 1's final video report for Virginia Tech's Embedded Systems Design course for summer 2017. Team 1 includes Jiaheng Tang, Vibhav Nanda, and myself, Tim Naclerio. The inspiration for our project comes from the growing field of autonomous vehicles. Currently, the main focus in this area is on highway and city driving. However, another area that needs to be explored is parking in parking lots and parking garages. Parking lots are often cluttered with people driving around in circles looking for the closest available spot. For our project, we created a realistic parking lot mapping system. So instead of circling around the parking lot, the cars can go directly to the first available spot. In order to implement this system, we broke our project down into three main components: the Scout Rover, the Consumer Rover, and the control system. The Scout Rover is tasked with driving around the parking lot. At each parking space, the Scout Rover will use a sonar sensor to check if the space is occupied by another vehicle or obstructed in any way. The Scout Rover then sends this information to the control system. The Scout Rover continues checking parking spaces until the entire parking lot is mapped. The Consumer Rover represents the user of the system. The control system sends the location of the nearest parking spot to the Consumer Rover. Consumer Rover then goes and parks in that spot. When the parking is complete, the Consumer Rover notifies the control system that the spot is no longer available. The control system receives sensor information from both rovers. It keeps track of each rover's location in the parking lot and the status of each parking spot. When the system first starts up, a command is sent to the Scout Rover to start mapping the parking lot. When the Scout has finished mapping the lot, a command is sent to the Consumer Rover to park in the nearest spot. The system then updates the availability of the spot where the Consumer Rover parks.
Hi, my name is Jiaheng Tang, and now I will talk about the system design aspect of our project. So this is a parking lot we use for our project. As we can see, there is a U-shaped black line that represents the main path of our project. Perpendicular to the U, there are some individual shorter black lines that represent individual parking spots. On some of the spots, there are some red blocks that represent the possible rovers that are taking up the spot. So the consumer rover cannot park at where the red blocks are. On the right, we have a Scout rover. Its job is to traverse through the parking lot and map the whole environment. On the left, we have a consumer rover. It's gonna wait on the instruction from the Raspberry Pi to go to the nearest parking spot and park there. So here is the block diagram represents how each of the components interact with each other. In the middle, we have a PIC32 microcontroller that are connected to all those different components. It's connected to the line following array and the ultrasonic sensor by the digital I/O pins. It's connected to the motor encoder by the motor shield connector. It's connected to the Wi-Fi by the wireless shield so that it can communicate with the Raspberry Pi via the UART. It also has some different modules like timers and LEDs on the board. So here is the Hcsl ultrasonic sensor we used on our Scout rover. We used it to detect whether a parking lot is empty or not. It has a detecting range from 2 centimeters to 4 meters, so it's perfectly suitable for our application. To get the distance data, it's very simple. We just need to apply a high voltage to the trick pin, and then measure the time it takes for the echo pin to go from high to low. So next, we have the QTR8Rc Reflectance Array that we used on each of our rover to detect black lines on white background. The sensor values is captured by measuring the time it takes for the pin to go from high to low. Since the white background is more reflective than the black, it takes shorter time for the IR to be reflected back. The values are then converted to 0 and 1 by comparing it with the threshold value. After that, we can use the converted value in our line following algorithm. So this is a Scout rover when we put all the sensors together. So here's a picture of that.
I'm Vibhav Nanda, and I would be talking about communication protocol, server, and graphical user interface. In terms of communication, there are two different types of message passing. The first type of message passing is internal message passing, which means passing information between threads of the firmware. Internal messages contain device ID byte, size byte, and data. Device ID byte indicates the origin of the message within the firmware. Size byte indicates how large the data is, and data placeholder contains the actual data. The second type of message passing is external message passing, which means relaying information between the rovers and the server. A typical external message contains a header byte, packet number byte, a size byte, and an internal message that the external message contains. The header byte and packet number byte are used to make the communication robust by keeping a track of packets and coming up with coping mechanisms in case packets are dropped. Now moving on to the server and graphical user interface. The graphical user interface has three main types of tabs, including Simulation tab, Rover Status tab, and Debug tab. It also has four different types of buttons, including a Start button, Stop button, Reset button, and a Demo button. This is a typical example of the Simulation tab. The Simulation tab is a virtual representation of the parking lot explained earlier. The black square represents the current position of the Scout rover. The gray square represents the current position of the consumer rover. A red rectangle represents a full parking spot. A green rectangle represents an empty parking spot. And a blue rectangle represents the parking spot used by the consumer rover. A rover status tab is used to visually see if the rovers are connected to the server or not, and also keep a track of the server status. The labels would change if either the server disconnected or one of the rovers disconnected. The third main type of the tab is a Debug tab, which is used for debugging purposes. It shows us the sensor data and state information of different threads. All of the information combined in this tab helps us to debug and understand the behavior of the firmware and sensors at any given time. We also have four main buttons as shown in the black circle on the right bottom corner. The Start button initiates the connection between the rovers and the server. The Stop button breaks the connection between the rover and the server. The Reset button resets the entire server and clears all the fields. And finally, the Demo button is used to send Scout rover an external message telling it to start moving.
My name is Tim Naclerio, and I will be covering the capabilities, limitations, and improvements for our project. Our project has many capabilities which can be broken into four categories. Overall, motors, sensors, and GUI, or graphical user interface. The overall system is designed to handle any configuration of parking spots in the parking lot. If the lot is full, the consumer rover will not move. Otherwise, the consumer rover will park in the nearest available spot. The motors in our system utilize pulse width modulation, or PWM, to control the speed of the rovers. A hardware timer is used to set a reference period for the PWM, and output compare modules are used to adjust the duty cycle. Encoders are attached directly to the rover's motors and send out a pulse every time the motor shaft turns 1/12 of a revolution. The number of pulses are counted and are converted into a distance traveled measurement, with centimeters as the unit of measurement. The sensors have the ability to calibrate each time the rover is reset. This allows for the rovers to adjust for differences in light and surface conditions. The GUI has the ability to show all the sensor data from the rovers in real time, as well as the state information. The information is also available for review after the system is stopped, which greatly helps with debugging of the system for any error that may happen. There are several limitations to our system. For starters, our system only allows for the current parking lot to work. If extra spaces were added, or if spaces were removed, the system would not work properly, because the GUI only displays the one parking lot. In addition to that, the parking spaces are always on the right. This is because the sonar sensor is only mounted on the right side of the rover, and because there is no differentiation between a parking space token and a right turn token. Also, since we are using a IR line follower array, if there is not enough contrast between white and black, the auto-calibration takes some time to get working. Lastly, sometimes there is a packet drop by the server if the previous packet is still being parsed. So if information from the rover is being sent too quickly, a packet will be dropped. Looking back on our project, we can improve it in a few ways. The first improvement that we would like to make with our project is to have the overall design allow for different parking lots to be loaded into the control system and GUI. This would make for a more practical system for real-world use. The next change that we would like to make is to use hardware timers with the encoders as a clock source instead of using the encoders as external interrupts. This would greatly improve our design as the system would have significantly less interrupts to deal with. The sensors could also be improved if the calibration process was changed slightly. The current method only calibrates on a reset and uses the first 10 values. To improve this process, we would average the last 10 readings so that as the light and surface changes, the calibration takes that into account. The last improvement for our system is actually reorganizing the code for the graphical user interface. The way the GUI was written didn't allow for much code reusability, so by restructuring the code and adding more comments, future changes to the system can be made much more easily. This concludes our final video presentation. Thank you for watching.